Hi guys, and welcome to this channel. On today's video, I would like to help develop somebody. I want to invest in someone's brain, knowledge, and experience within these simulations. I also want to add value to someone who wants to probably start a water business. This is the right platform for you. I'm going to try my best to upload as many as possible tutorials related to practical real-life examples. On today's video, I want us to look at a dimin plant, a demineralized water system. For this plant, we are going to use the DW simulation to simulate our plant. It might be limited in terms of the minerals that we might be able to add here, but that's not a worry. If you have access to Aspen, that will be great. For now, let us work with what we have, and we are going to use the simulation. I'm going to try as much as possible to use visuals to explain what I'm talking about and also the practicality of it. Okay, guys, so the first question would be, what is a dimin plant? Well, a dimin plant typically takes water that has a very high concentration, high conductivity, high almost impurities as much as possible, usually from the reservoir, tap water, underground water maybe, and tries to purify it to remove the minerals and make them as close to zero as possible. So, for example, say for this scenario, our water has the following constituents. In terms of minerals, it could have been more, but just for now, for the sake of this example, say we have chlorine, magnesium, sodium, sulfate, and nitrate at 25 milligrams per liter, magnesium at that, obviously sodium as well, and so on and so forth. This will definitely then have to go into our demineralized version of a cation. We are going to dose sodium hydroxide and 42% into the anion resin to achieve a very low conductivity of less than 5. Industrial plants could have been lower for lab and serious analytical results, but because we just probably wanted for the mixing of the following spec, our minerals must be as close to zero as possible. Typically, we want everything to be 0.1, unless probably we can give some exceptions to sulfate and nitrate. Those ones can be at least at 1 or less milligrams per liter, but overall, we want everything to be as close to zero as possible. So we are going to conduct this plant together ourselves using DW simulation. And this is what we are going to do step by step together. This will represent the cation, this will represent the anion. So basically what you just saw, we are going to try and simulate it ourselves using DWSIM. Okay, let us start step by step together. For the simulation, let us add all the ions that we would like to have in our water. Because we are limited in terms of functionality, this simulation, DWSIM, does not have all the ions and the minerals we want to add. Let's work with what we have. But practically in a real life example, you definitely want to add all the ions that you have as much as possible. So I'm going to click on next. I'm just going to search ions. And these are all the ions that this simulation has, which is very great. Let us firstly start by adding our chloride. I'll also like to add our magnesium. Let us add our sodium as well. Let's add the sulfate ion. Let us add the nitrate ion. And if your water content has potassium, lithium, iodine, all these ions that you see here, add them respectively. For the sake of this example, I'm just going to add these few ions, and assuming that the water inlet or our raw water from either the tap or reservoir has all these contents. Now let us click next. It's going to guide you in terms of what we can use. Firstly, actually, let's go back. Our compounds. Okay, we'll definitely go back. So I'm going to add my ideal. So it's limiting us here. It's okay. Add and add. Next. Now let us select our units that we'd like to use. I would like to use, let's see, I think this will work. Our SI engineering units will work. Let's see, bars, degrees Celsius. What else? Flow rate. Okay, that's perfect. This will work. And if you're not happy and you'd like to change some of them, you can create your own and customize it according to the units that you feel like you best understand. Now let's finalize. Next, finish. So this is typically our simulation when it's empty, there's nothing on it. I actually want to go back. There's some few things that we also want to add that I didn't add here. Let us add our hydrochloric acid and sodium hydroxide as well. Hydrogen chloride and NaOH. Sodium hydroxide. There we go. So we've added everything. I still want to see if it's going to limit us when it comes to the thermodynamic properties. Can we also please add nRT? Let's add it. Perfect. Now we have everything. So all I did here, guys, was add our compounds, which are the following. Here's the compounds that we'll be working with here. And then in terms of thermodynamic properties, here are our three specific thermodynamic properties that we can work with. Let us start with our simulation. Again, let me remind you, we are trying to build a simulation system for our demineralized water that has no minerals. So we are going to have an inlet stream with a high quantity of minerals and ions and an outlet of as less as possible minerals and ions. Before we start, guys, let us look at our raw water inlet stream. Assume that our raw water inlet stream has the following quantities. Tap water typically has a conductivity between maybe 80 microsiemens per centimeter to all up to 800 microsiemens. So it's up to you on what conductivity your water has. I'm just going to assume our water probably has a conductivity of 500 microsiemens per centimeter. And then in terms of the minerals in my water, of course, we can have water has so many constituents that makes it up. It's not just the H2O. There's some ions that are in there in terms of concentration. So for the sake of this example, we have chlorine at 25 milligrams per liter. We have magnesium at 17.15 milligrams per liter, sodium, sulfate, and nitrate respectively also at the following values. You will notice that when we build our simulation, let us start with our inlet stream. So for our inlet stream, I want our inlet stream to enter at 25 degrees Celsius. Let us say 2 bar. And here we can make it just 7.5 kilograms. And then in terms of our compounds, let me clear this. We are going to specify what we have. Let us say and I want to specify in terms of molarities because this is going to be in milligrams per liter, right? The solvent here, it's definitely the water. We didn't add it. My apologies. Let us go back and add the water settings. Compounds, H2O. And that would be water. Why is it not popping up? Water. There we go. So we also have water in there. Let us clear. I want to express everything in a form of molarities with the solvent being water. So all these molarities or concentrations will be the constituents that are inside of our water. Remember I said this is what's in our water in milligrams per liter, but you'll notice that unfortunately DWSIM uses mole per liter. So we need to convert from milligram per liter to mole per liter using the molar mass. And this is how we are going to do it. The first thing we are going to do is, I preferred first convert this to that from milligrams per liter to just grams per liter by dividing by 1,000. And then we just have in terms of grams per liter. From grams per liter, I also introduced the molar mass. So the molar mass of chlorine, magnesium, sodium, sulfate, and nitrate. Now to get our molarities, to convert from grams per liter to mole per liter, all you have to do is you just have to divide your grams per liter by the molar mass. If you divide the grams per liter by the molar mass, you are going to get your molarity. This is just a simple conversion from milligrams per liter to mole per liter. And just to express in form of molarity, molarity is basically concentration. Back to our simulation. I hope I'm not losing anyone. I want you to benefit as much as possible. So for our molarity, we have these values that we are basically going to punch in, which is this, that, and that. Now let us type everything in. So the first thing I did was basically clear everything and then accept the changes. Hence it populated this 55. Now let us go ahead and computing our figures. Accept changes. There we go. So the first thing that you do here, just to make sure that we are all on the same page, clear everything. It goes to 0. Then you accept the changes. Click solve. It will populate this number here. Then afterwards, only then you can compute your concentrations. And if you're wondering how did that number populate itself, basically we can assume that for 1 liter of water, it weighs 1,000 grams, which is basically 1 milligrams per liter in density, or 1,000 kilograms in terms of density, kilograms per meter cubed. If we divide that by its molar mass, it gives us 55.5. That's how the simulation also got its figure here. Let us title this raw water. And in terms of mole fractions, we basically have 0.9999% of water, and very small percentages are there of our ions. Basically, we are just telling this stream here that water is purely entering with small constituents, making it up as well, adding to its impurities. In terms of molarities, our concentrations, these are the figures that we have in terms of mole per liter, and that for water as well. I hope you guys get it right. In simple terms, this is basically what we have in molar fractions. We have 99% of water entering, and the 1%, it's all the impurities. But in terms of molarities, or concentration rather, this is what we have. Okay, let us continue. I would like to just name this here, accept changes, solve, let's see, all water inlet stream. There we go. I would like to also insert a property table. Let's just add it here. Our property table will include the temperature, the pressure. Let us include our molarities, mixture, and would like to include chloride, magnesium, sodium, sulfate, nitrate, and water itself. This stream does not have any hydrogen, chloride, or any base, the sodium hydroxide in it. Hence, they are not included. Enter. Let's go. There we go. Now, the next equipment that we are going to add, typically in a demineralized water, your water will mix with these particular chemicals. The first one being the cation, and that will be our acid, and then the next one will be the anion, which is the base. Resins are used for the regeneration of water. For the sake of the simulation, we can also add mixes, which will similarly play a similar role. So that will be our mixing stream. Let us give our mixer a name. We are going to title this mixer cation, because this will be the cation resin. Let us give this particular stream a name and call it hydrochloric acid. Entering at roughly 25%. The temperature here, I'm going to leave it at 25 degrees Celsius. The temperature, I'll leave it. Let us give this also just a nod to hydrofluoride. 15 will do. For our compounds, I want us to clear everything here. we are only going to specify in the terms of mole fraction. We are going to have 25% of the hydrochloric acid. Use the commas, guys, use the commas. And here we are simply going to have the balance, which is 0.75%. So we are adding 25% hydrochloric acid diluted with water, hence a fraction of 25 and 0.75. I'm just going to press enter. I'm going to say accept and then run my file. Perfect. Now let us also add a table here. So I'm going to say insert the master property table. This will be for our hydrochloric acid. Specifically, we want to see the temperature, pressure, as well as the mole fraction, the mixture. Or the molar fraction. I would like to see hydrochloric acid, which is hydrogen chloride. Okay. Okay, so this is the second stream. Perfect. Let us now feed this fourth stream into another mixer. Now this mixer, it's not an ordinary mixer. It is going to replicate an anion resin. So we are going to name it and say anion. Here we are going to have our base, which will be the sodium hydroxide. The sodium hydroxide is going to enter also roughly at 15. This time around, clear again. Let us feed our concentration here at 42% and the balance. There's an error with stream 7. Okay. But meanwhile, let us save this. I'm also going to insert here a table. This will be for the base. You want to see the temperature, pressure, and the molar fraction. Let it be for the base, and that's sodium hydroxide. I just want to rename this to base and a fraction of 0.42. So stream 7, we want it to be the Demon water. I'm going to change the property package to NRT and then say solve. There we go. Also, let us insert its property package. Now this is our final water. We want to see the quality of our water. Can I just exit here? Now we want to see the final property of our water. And firstly, let's rename the stream to Demon water outlet stream. I would like to see temperature, pressure, and the molarities. So that will be chloride, magnesium, sodium, sulfate, nitrate. There we go. Exit. Oh wow, this is amazing. Okay, so there's a trick here. Our molarity, it's showing in terms of mole per meter cubed. Let us go to settings and change that. Units, molarity, molar concentration. I'm going to change it to Let us create new. So we want to see temperature in the form of this, that, and then molarity to be mole per liter. I hope we're not missing anything. Good, yeah, that's what we want. Create new. Let us use that. Mole per liter. Perfect. Good, there we go. This is amazing, guys. This is truly, truly good. Okay, let me just remove water here. It's pretty much not necessary. Good. So this is what we are feeding, and this is what comes out. So you already can see that there was a reduction, right? It did reduce. Now I want us to convert these figures here into something that we can physically read in terms of ppm or milligrams per liter. So let's convert all these numbers for ourselves. Just going to take a nice screenshot so we don't have to continuously refer. So basically, this is what we have. I'm going to punch in here. Use commas, guys. Use commas. Same thing here. It's going to be 1,35931E. This is amazing, guys. This is amazing. Then we are going to have 1. Okay, guys, so basically what we have here is that we basically fed water with the following concentrations, and after demineralizing it, our water left at this small constituents 0.04, 0.003, 0. So everything is less than 0.1, which is fantastic. So typically that's how your dimming plant would work. You feed higher concentrations in your water, and they come out at as low as possible, as close to zero as possible. So for a diamond plant, we try to remove minerals as much as possible. We don't want to see any minerals in it, hence it's called demineralized water. Your minerals must be as close to zero as possible for your water treatment plant. I hope this makes sense. And if you are an engineer trying to start your own consultation company, this is a very great way to start. I hope this really did add value to you guys. If you're considering starting your own water treatment plant, I hope this is something, a great start or a great foundation rather for you, to use such principles to help you to plan ahead or to pre-calculate your results before you even do it practically or industrially. This is why we have simulations. They help us simulate plants practically using a software before we do it practically at the industry itself. So I'm going to try my best to continuously add value and help you guys build and develop yourselves to greater heights. Thank you so much for watching. Till next time. Bye.